cover our chapter number 4. And this chapter, and also chapter number 5, the chapter number 4 is on other equations of state. Uh, if you remember, in chapter 3, we discussed the compressibility equation of a state for the ideal gas, and then we corrected for the real gas behavior. But if you noticed, in those application of those equations of states requires the readings from the z charts, going finding the z values. So it's not that easy to work with if you want to program this phase behavior studies in some sort of a numerical simulation. So to accommodate that, there are different equations of a state developed. Okay, and these equations of states are basically used such that developed such that it can be used in the numerical simulations. One of the most famous equations of a state developed is called van der Waals equation of a state. Okay, so the van der Waals equation of a state is very similar to our compressibility equation of a state. Okay, the only difference is here the van der Waals tried to get rid of the assumptions that we made during development of the ideal gas. Okay, so if you look at this equation, this is basically some sort of a pressure times some sort of a volume, PV, being equal to RT. So it's basically very similar to our ideal gas equation of a state. However, if you see, there are two extra terms. So the pressure has been added by this A over Vm square, okay? And there is a B, constant B, subtracted from the molar volume, okay? So the first correction here on the pressure is to incorporate the intermolecular forces, okay? Because as we have, because in the ideal gas equation of a state, we ignored all the intermolecular forces, attractive and repulsive forces. But here, by adding this A over Vm square, which A is a constant and Vm is the molar volume of the fluid, and by adding this, we are trying to basically correct the pressure for forces of attraction, okay, between the molecules, okay. So the actual pressure exerted on the walls of the vessel by the real gas is less by the amount of A over Vm square than the pressure exerted on ideal gas, okay. So this A over Vm square is trying to get rid of that assumption. And then if you remember, we said in the case of the ideal gas, we are assuming the molecules, the gas molecules, they don't take any volume, or the volume associated with the gas molecules are negligible in compared to the total volume of the mixture. So here this B is basically tries to correct that by subtracting the volumes related to the actual molecules. So the constant B is regarded as a correction to the molar volume due to the volume occupied by the actual molecules. So constants A and B, so in this equation, again, pressure, we know Vm, pressure, Vm, RT. There are two unknowns, A and B, okay, which we need to find for a particular gas. Okay. Generally, this equation, the van der Waals equation of a state, is valid at low pressures, okay. When your pressure is low, this van der Waals equation of a state works really good, but at a higher pressure, it starts having more inaccuracy, okay. So I don't expect you to memorize the van der Waals equation of a state. However, you need to know, if I give you the van der Waals equation of a state, you need to know each one of these terms, what are they, what they are doing, what they are standing for. So the A over Vm square stands for correction for the intermolecular forces, and the B is correction for the volume of the molecules. Okay. But as you can see in this equation, the intermolecular forces is only related to the volume, okay? However, we know the intermolecular forces also impacts the temperature, or temperature impacts the intermolecular forces, okay? So there is a dependency on temperature and the molecular attraction as well. So RK, or later on we call it SRK, because Rich and Kong, they start developing this equation, and at the same time, so independently was working on the same equation. they come up to they develop these two equations which are very similar. So people refer to this as SRK equation of a state. So the difference between SRK equation of a state and the van der Waals is in the intermolecular forces, they try to bring the effect of temperature as well. Okay. So again, this is P, this is some sort of a P times volume equal to RT. The minus P is the same as van der Waals trying to correct for the volumes occupied by the molecules. And this term is basically added to take into the account the effect of temperature. Okay. So again, T square root of temperature, molar volume, and the same B constant. Okay. So SRK equation of a state is good. We usually use that. Sometimes we use that in unconventional reservoirs as well. Okay. But later on, I'll show you how to get these A and B values because we need to have them for every gas and to be able to use this equation. The next equation of a state is a Peng-Robinson equation of a state, and actually this is the most common equation of a state used in oil and gas industry. Okay, and as we will see in our lab, the PBT lab is also written based on the Peng-Robinson equation of a state. It's a more complicated equation in compared to SRK equation of a state. However, it's more accurate in the case of oil and gas. Okay, so again, some sort of a pressure times some sort of a volume equal to RT. For this time, the intermolecular forces correction is more complicated than the van der Waals and the SRK equation of a state. So again, you don't need to memorize this. The only thing is you need to, if you see the equation, you should be able to recognize this is a Peng-Robinson equation of a state, and you should be able to describe these extra terms and their application. Okay, so how do we get these two constants of A and B? Okay, if you go back to the chapter 2 where we were studying the behavior of the pure gases, the pressure versus some sort of a volume, and you see that if the pressure was dropping significantly with a small change in the volume, and then it was plateau because the pure component till all the liquid goes to the gas, and then it was going down. If we repeat this in different temperatures, then we could have this two-phase region. Okay, so if I look at the, let's say, the van der Waals equation of a state. Okay, so to get these two unknowns, A and B, what I'm going to do, I'm going to use the property of the critical point. Okay, so the critical point is the point that these two bubble point and the dew point line meets. So at one point, at the critical point, basically we will not get into the two-phase region, but we become tangent to the two-phase region, and then it goes down. This point C mathematically has a very important characteristics. Basically, the first and the second derivative at point C, at the critical point, is equal to 0. Okay, so that's called saddle point. So at this point, the first and the second derivative is equal to 0. So if I take the derivative of pressure with respect to volume and put it equal to 0 for the first and second derivative, then I will have two extra equations. So this is my van der Waals equation. This is the first derivative, and this is the second derivative. And now, since this is at the critical point, I know the temperature is the critical temperature of the pure component, whatever component that I'm studying. The volume also associated with the critical, so it's a molar volume at the critical point for that gas. So R is a universal gas constant. So I know the R, I know the TC, I know the VMC, and the only unknown in this equation is A and B. The same goes for the second derivative. Again, R, TC, VMC, I know it, the only unknowns are A and B. So I have two equations and two unknowns that I can solve. So if I solve that, you can see the A constant A becomes 27 R squared, critical temperature squared, divided by 64 critical pressure, and B is RTC over 8 PC. So A and B are basically constants and related to the critical properties of the pure component. So this way, we don't even need to go and read the Z factors. Okay, so but this has application in numerical simulation. So when we do the numerical simulation and we use the PBT equation, we use Peng-Robinson equation, and this is how we are going to come up with those constants. Okay. But in our class, we are going to use the compressibility equation of state. Okay. So in the next video, we are starting the chapter 5, which is the 5 reservoir fluids. We are going to see what type of reservoir fluids now we have that we can go and study their behavior one by one.